Hello everyone, welcome back to my channel. So in this video, I am going to discuss the question paper and answer of the ETO COC exam March 2024. You can skip this video if you are not preparing for this exam. This is only for the exam preparation for the ETO COC. Okay, so let us start the discussion for the question paper of Electro Technical Officer COC written exam. Paper is Function, Electrical, Electronics and Control Engineering, Marine Electro Technology and SSCP. Total marks is 100 marks and 3 hours. Section 1, 3 questions. So let us start with the question number 1. Explain why it is necessary to have reverse power protection for alternators intended for operation. B. Sketch a reverse power trip. Briefly explain the principle on which the operation of this power trip is based and how tripping is activated. The answer of this question is available in Rahul page 29 in my notes, and also MET 68 page number. So this is question in my notes, and here is the answer. When two or more alternators are operating in parallel to meet ship's power demand, it is possible that one of the prime mover may experience some fault, maybe loss of fuel or the some other problems, and that alternator will no longer supply ship's load. The faulty generator set will not stop. Instead, it will start taking power from the bus bar running in same direction and same frequency. The generator is now acting as a synchronous motor. The faulted set must be stopped by tripping its circuit breaker and disconnecting it from the bus bar. Damage may be caused to prime mover, example due to failure of lubricating oil system or the high speed. The remaining healthy generator might get overloaded, supplying both ship's load and faulted set. Regulation states that when two or more generators are working in parallel to supply ship's electrical demand, each must be fitted with reverse power protection. In event of reverse power, fault is sensed by the reverse power relay, which then closes the contact which is connected to ACB circuit for tripping. This de-energizes the no-volt coil to release the latch and trips the ACB. Its construction is similar to electricity supply meter. The lightweight non-magnetic aluminum disc mounted to a spindle which has low friction bearing is positioned in a gap between two electromagnets. Upper has voltage coil connected through a transformer between one phase and artificial neutral of the alternator. Lower electromagnet has current coil supplied from same phase through a transformer. Magnetic field is produced by both voltage and current coil. Both field passes through aluminum disc and causes eddy current. The effect of eddy current is torque produced in the disc. With normal power flow, trip contacts on spindles are open. When power reversed, disc rotates in a other direction. Away from stop and contacts are closed, so breaker trip circuit is energized. So here is the diagram. You can see there is two coil. One is from potential transformer and one is from CT. And this is the disc which rotates. When the normal power supply is flowing, the disc is rotating in one direction. But when the reverse power is flowing, it will rotate in opposite direction and it will go and trip the trip circuit. On switch will be there that will be activated once the spindle is rotating in other direction. Let's move on to question number 2a. Describe a brushless alternator with AC exciter, static AVR. State the output voltage characteristic for this type of machine. The answer of this question is available in another PDF with the name MET 1 year in page number 5. So let's go to MET 1 year, page number 5. This is a question, same question. And here is the diagram for the alternator with static AVR. The alternator is producing voltage here. It is going to the sensing element of AVR. And this is the exciter circuit. This is the field winding for the alternator, and based on comparison, value of this field will be increased, and in the result the three-phase supply produced here for the DC supply will be increased. And here the AC supply, three-phase supply produced by the exciter rotor is converted into DC supply by three-phase rotating diode, and it is fed to the alternator. So let's read the answer what is given here. In this machine, slip rings and brushes are eliminated and excitation is provided not by conventional direct current exciter but a small alternator. The AC exciter has unusual arrangement for three-phase output windings on the rotor and magnetic poles fixed in the casing. The main rotor has residual magnetism which produces a weak magnetic field. Therefore, when rotor turns, this weak field flux cuts the main stator winding and a low voltage is generated in the main stator. This output is fed back to AVR which rectifies the AC power to DC. This DC is fed to the exciter stator. The stationary magnetic field is created in exciter stator by DC fed to it. The exciter rotor, when it rotates, cuts the stationary field.
Since the exciter rotor windings are wound to produce three-phase AC power, three-phase AC is generated in it. All of this three-phase AC is led to bank of a rotating diodes mounted on the same shaft. The diodes convert all of this AC to DC. This DC is the excitation of the main generator. This DC in the main rotor adds to the weak magnetic field already there due to residual magnetism of the main rotor. So the total flux produced by the generator rotor is now increased field flux due to current feedback from AVR and field flux due to residual magnetism. Since more flux now cuts the generator stator winding, a higher voltage is generated. This process of voltage buildup continues until the generator rated terminal voltage, usually 440, is reached. The AVR regulates the voltage to this value. State the output voltage characteristic for this type of machine. So this is the graph for the typical voltage dip recovery pattern of an alternator, and in this graph we can see different diagrams here. Let's read what is given. Both the conventional alternator with DC excitation carbon pine regulator combination and the brushless machine described have error operated AVR and excitation system. The voltage has to change for the AVR to register the deviation from normal and then to adjust the excitation for correction. The suddenness of initial voltage dip is such that the response from the error operated system cannot come until the dip is in the second slower stage. Thus, neither machine can prevent the rapid and vertical volt dip due to transient reactance, but the faster acting voltage regulator of brushless machine will arrest the voltage drop sooner or on the slower secondary part of this descent. The carbon pile regulator is slow compared with the static type, but better recovery by brushless alternator is also achieved by field forcing, that is boosting the excitation to give a quick build-up. AVR will control the generator voltage to plus minus 2.5% of its set value over the load range. This is steady state voltage regulation. Transient voltage dip is usually limited to 15% for a specified sudden load change with recovery to rated voltage within 1.5 seconds. So in this diagram with different types of AVR, how the voltage dip takes place and how it is recovered when a sudden load changes or the voltage dip takes place.
Let's move on to next question 3a. Which of the following devices will prevent a DC generator from becoming motorized? Option A, overcurrent relay. Option B, motorization trip. Option 3, reverse power relay. Option 4, reverse current relay. This question was also asked in January 2023 paper. In B, give a detailed explanation as to why other options were not considered. You can find the answer of this question in Rahul page 85. Let's go to my notes in page 85. The same question, answer is here. Let's move on to option A, explanation. Over current relay. An OCR is a relay which will come into operation only when the current magnitude is higher than the set value of the relay, and so this is not useful to detect motoring effect. Let's move on to B, motorization trip. A motorization trip will work only when generator starts turning in opposite direction, and if that happens it is already late and damage is done. Reverse power relay. Reverse power relay works only on AC generators since they are set for power values. It should be understood that the load current is alternating in phase winding and the load current has no direction. In alternator, instantaneous value of voltage and current is changes from positive to negative and not constant. However, vector value of current and voltage are constant, but direction is governed by the effective power passing through stator winding, and their direction can change during fault. Option D, reverse current relay. In DC generator, the line current direction is constant. If two generators are running in parallel and one of the set experience a fault in its prime mover, its RPM will start to reduce and terminal voltage will also reduces, causing a line current to flow in the armature of faulty generator. This will cause motoring action and will produce torque of opposite direction, which could damage the coupling or shaft. Reverse current relay will sense this and trip the generator from bus bar. Let's move on to section 2, question 4a. What is commutator? Discuss its rectifying action in details. B. Determine the line current taken by a 440 volt 3-phase star connected motor having an output of 45 kW at 0.88 lagging power factor and an efficiency of 93%. 10 mark question for numerical and 6 marks for the theory. So let's start with the what is commutator. So in the chat GPT answer is given. Commutator is a crucial component found in certain types of electrical machines, including DC motor and generators. It consists of segmented metal ring mounted on the armature shaft of the machine. The segments, known as commutator bars, are insulated from each other and connect to ends of armature winding coil. The function of commutator is to facilitate the reversal of current direction in armature coils as the rotor rotates in DC machine. This reversal of current ensures that the magnetic field produced by armature remains in the same direction related to magnetic field produced by the field windings, thereby maintaining the direction of rotation of the motor or generator. In a DC motor, commutator helps to produce continuous and unidirectional torque output by ensuring that the armature current always flows in the same direction through the rotor windings regardless of the rotor position. In DC generator, commutator converts the alternating current in induced armature coils by rotating magnetic field into direct current by periodically reversing the direction of armature flow in the armature coils. This results in a direct current output from the generator. Now discuss the rectifying action. The rectifying action of a commutator refers to its ability to convert alternating current induced in the armature coil of a DC generator into direct current output. This process occurs due to segmented nature of the commutator and the way it interacts with the armature winding and the magnetic field. In DC generator, as the armature rotates within the magnetic field produced by the field windings, alternating current is induced in the armature coils. So already same thing is explained in the above answer also what is commutator. You don't have to write all of these things because it's a very long answer. Just write some important points, the definition of what is commutator and then what is the primary function, and then directly come on to the rectifying action of the commutator. So where it is used and why it is used, that's all. Because it is only a 6 mark question, so you have to manage your time, you have to write answer that much only where it is how much it is required, and you should be able to complete your paper in 3 hours of time. So according to marks, you have to write the that much lengthy answers. Let's move on to the numerical part, section B. It's a very simple question, and answer is also very simple and very short, just 2 to 3 minutes only required. So you already given efficiency is given, that is 93%, and output is given 45 kilowatt. So you can calculate the input from here. So input is output by efficiency. You are getting 48.3 kilowatt. Now they are asking what is the line current. So we'll know the formula for the power, root 3 into VL into I into cos phi. P we already know from here. We got line voltage is 440 and cos phi power factor is given 0.88. So we can easily calculate the current I from here. So we are getting 72.15 amps. Very simple questions. Next question 5a. Describe the effects of change in speed, rotor current and torque as load is applied to the induction motor. How does the motor adjust its stator current with change in mechanical load? When a load is applied to induction motor, several effects occur in terms of speed, rotor current and torque. Speed. Initially, when the load is applied to an induction motor, its speed tends to decrease. This decrease occurs because the torque required to drive the load exceeds the available torque from the motor. As a result, motor slows down to a speed where the available torque matches the load torque. This new operating speed is usually lower than the motor's synchronous speed, which is the speed of the rotating magnetic field produced by the stator. Effect on rotor current. With an increase in load, rotor current of induction motor typically increases. This increase in rotor current is necessary to produce the additional torque required to overcome the load. The increased rotor current leads to a stronger magnetic field in the rotor, which interacts with the rotating magnetic field in the stator to produce the required torque. The rotor current also causes increased loss in motors such as copper loss and rotor copper losses. As the load of the motor increases, the torque output of the motor must also increase to match the torque demand of the load. The motor adjusts its torque output by increasing the rotor current as mentioned earlier. This increase in torque allows the motor to maintain its operating speed while driving the load. The torque developed by the motor is directly proportional to the rotor current and the strength of the magnetic field produced by the interaction between stator and the rotor fields. In summary, when a load is applied to an induction motor, its speed decreases, rotor current increases, and torque output adjusts to match the torque demand of the load. These adjustments allow the motor to continue operating and drive the load effectively. Next question is, how does the motor adjust its stator current with change in mechanical load? So in an induction motor, stator current adjusts automatically in response to changes in mechanical load. This adjustment is facilitated by interaction between rotor and stator magnetic field, which governs the motor's operation through the principle of electromagnetic induction. Change in speed as the mechanical load increases. This part is already explained earlier. Rotor current also already explained earlier. Back EMF and stator current. The rotor current induces a counter electromotive force known as rotor's back EMF. This back EMF opposes the applied voltage and limits the stator current to a level that maintains the balance between electromagnetic torque and mechanical load torque. As the mechanical load increases, the back EMF decreases, allowing more stator current to flow to maintain torque balance. So, in summary, when the mechanical load on induction motor changes, the adjustment in stator current occurs indirectly through the induction of rotor current, which in turn affects the electromagnetic interaction between the rotor and stator fields, thereby adjusting the motor's torque output to match the mechanical load. Question number 5b. A 20 kVA 2000 by 220 volt single phase transformer has its primary resistance of 2.1 ohm and a secondary resistance of 0.026 ohm. The corresponding leakage reactance are 2.5 and 0.03 ohm. Estimate the regulations at full load under power factor conditions of number 1 unity, number 2 0.5 lagging, and number 3 0.5 leading. This question was asked in January 2024, just 2 months back question paper, and I have discussed this question in my that video of the January month. Question 6a. Which of the following three motors has the poorest speed regulations? Shunt motor, series motor, and cumulative compound motors, and explain. It's a 6 mark question, theory question. Let's see the answer from the chat GPT. Among the three types of motors mentioned, the series motor typically has poorest speed regulation. Here is why. Series motor explanation. In a series motor, the field winding is connected in series with the armature winding. As a result, the field current is directly proportional to the armature current. When the load on the motor changes, causing the armature current to increase or decrease, the field strength also changes proportionally. This characteristic makes the series motor highly sensitive to changes in load, resulting in poor speed regulations. Under no load conditions, the series motor can achieve very high speeds, but as the load increases, the speed drops significantly. Let's see the explanation of the shunt motor. In shunt motor, the field winding is connected in parallel with the armature winding. The field current remains relatively constant regardless of change in armature current or load. This characteristic provides better speed regulations compared to series motor because of field strength, and hence the magnetic flux remains constant, resulting in a relatively stable speed even with changes in load. Now, what about the cumulative compound motor? In cumulative compound motor, both a series and a field winding and a shunt field windings are employed. The series field winding adds to the flux produced by the shunt field winding. This arrangement provides better speed regulation compared to the pure series motor but may not be as good as shunt motor. The compound motor combines the characteristic of both series and shunt motor, offering moderate speed regulations. In summary, series motor typically has the poorest speed regulations among the three types of motor due to its high sensitivity to changes in load, which directly affects the field strength and consequently this motor's speed. Next question is numerical part B. An 18.65 kilowatt, 4 pole 50 Hz, 3 phase induction motor has friction and windage losses of 2.5% of the output. The full load slip is 4%. Compute the full load, that is rotor copper loss and rotor input. Second, shaft torque and the gross electromagnetic torque. This answer is available in my notes. The page number is 8. Number 8 page number. Same question is here. I have solved it before my preparations. So in this question, given data is power 18.65, 4 pole, 50 hertz, and 4% is the slip. So we all know slip is ns minus nr by ns into 100. So this part is already given 4%. So at least we can calculate nr from there. So this is the formula. All the values put in the formula. We are getting nr is equal to 1440. Nr is speed of the rotor. Now see how the distribution of the power takes place. Like how the power it comes to input. What are the losses? So first input power is given to the stator. Then there is stator iron and copper loss. Then there is that power, that is motor input minus loss, that goes to rotor input. Now there will be rotor copper loss and then winding friction loss. Then what comes outside is motor output, and after all everything mechanical power, that is gross torque. So few formulas, if you know, this questions will be very easy to solve. First of all, rotor copper loss in the terms of slip and PM, rotor input in terms of rotor copper loss and PM, shaft torque and gross torque. These four formulas you remember, you can solve this question. So in this first question is question number A, full load copper loss. Now you see the formula of rotor full load copper loss is S by 1 by S into PM. P is total power, motor output power. So now we already have the formula. Now we can find the total mechanical power developed. So motor output plus loss, that will give the total mechanical power developed by the motor. Now in the question it is given that 18.65 is the motor output and 2.5% is the loss. So 2.5% of 18.65 plus 18.65, it will give the total mechanical power developed, that is 19.11 kilowatt. And we can put this value in the formula of this formula. So we can get the rotor copper loss. So here is the solution. Full load copper loss 0.04 is the slip by 1 minus 0.04 into 19.11, we are getting 796.81 watt. Now second question is rotor input. Now see, rotor input formula, rotor copper loss plus PM. So what is rotor copper loss? So we already calculated rotor copper loss in part A. So this is 796 plus PM. PM we calculated from here. So we can add 796.81 plus this is kilowatt, 19 kilowatt. So we will multiply with 1000. So 19116.25. We are getting 19,912.76 watt. Third one is shaft torque. So shaft torque formula is this P out into 60 by 2 pi n. So P out is 18.6. This is a total output power. So put in the formula, we are getting 123.67 Newton meter. Now total gross torque formula is PM into 60 by 2 pi n. What we have PM? PM is 19.11 kilowatt into 60 by 2 pi n. We are getting as 126.76 Newton meter. This question might seem complicated, so many terms are there, but if you know the very basics, what are the motor input, the power is supplied to the stator, then there is stator and copper loss, then that this minus this, it is input to the rotor, then there is rotor copper loss, then there is winding and friction loss, then total motor output. If you understand all these concepts, then and then remember these four formulas, then it will be easy to solve this question. Let's move on to the last section, section 3, question number 7. With reference to gravity, Lifeboat David, state the purpose of the following. Option A, centrifugal brake. Question number 2, dead man's handle. Question 3, David limit switch. First option, gravity lifeboat davits are mechanism used for launching lifeboats from ships in emergency situations. These davits utilize the force of gravity to lower the lifeboat from its stored position on the ship's deck to water below. The centrifugal brake is a critical component of these davits and serves the purpose of controlling the descent speed of the lifeboat during the launching process. Let's understand how this centrifugal brakes operates. You don't have to write all this much of answer, just pick up one or two lines from each point. So what is the operating principle? The centrifugal brake operates based on the principle of centrifugal force, which is the outward force experienced by an object moving in a circular path. As the lifeboat begins to descend, the centrifugal brake engages to slow down the lowering speed. How the braking takes place? Typically, the centrifugal brake consists of brake shoes or the pads that are designed to make contact with a braking surface when the lifeboat is in motion. This braking surface is usually integrated into David systems. Centrifugal force activation. As the lifeboat descends, it generates centrifugal force due to its circular motion around the David's pivot point. This centrifugal force acts on the brake shoe, causing them to move outward and make contact with the braking surface. Now, fourth point, frictional resistance. When the brake shoes make contact with the braking surface, friction is generated between them. This friction creates a resistance force that opposes the motion of the lifeboat, thereby slowing down its descent. Controlled descent. By adjusting the design of the centrifugal brake components, including the materials used and the contact pressure between the brake shoes and braking surface, descent speed of the lifeboat can be carefully controlled. This ensures that lifeboat is lowered safely and smoothly into the water without excessive speed or abrupt stops. Safety consideration. The centrifugal brake is essential for preventing the lifeboat from free falling into the water, which could endanger the occupants or cause damage to the lifeboat itself. It provides a controlled descent even in rough sea conditions or when the ship is moving. Overall, the centrifugal brake is a crucial safety feature of gravity lifeboat davits, ensuring the safe deployment of lifeboats during emergency situation at sea. Now, use of deadman's handle. A deadman handle, also known as deadman's switch or deadman's control, is a safety mechanism commonly used in various applications, including transportation system and machinery. Its primary purpose is to ensure that device or system remains operational only when continuously controlled by an operator. If the operator becomes incapacitated or released from the control, deadman handle activates a safety measure such as stopping the machine or triggering a emergency shutdown. The deadman handles typically consist of a lever button or a switch that operator must hold down or engage in continuously while operating the equipment. As long as the operator maintains contact with the handle, system remains active. Safety features. The deadman handle serves as a safety feature to prevent accident caused by the operator losing control of the equipment due to unconsciousness, injury, or other incapacitation. If the operator lets go of the handle, it triggers a safety response to stop the machine or activate emergency procedures. Transportation systems. Actually, this is a generic statement about the deadman switch. Otherwise, the function is same in our lifeboat, rescue boat also. Transportation system. Handles are commonly found in transportation systems, trains, trams, elevators, etc. So this is a generic lines. Machinery and equipment. Deadman handle are also used in various type of machinery and industrial equipment. Emergency situations. In emergency situations, deadman handles can play a vital role in preventing further harm or damage. For example, in a factory setting, if your operator becomes unconscious while operating heavy machinery, the deck handles can automatically shut down the equipment. So in the rescue boat also, that handle, if the operator who is operating the rescue boat, if he is unconscious or he falls down in the water, then that switch will operate and it will stop the engine. Overall, the deadman's handle is a simple yet effective safety device designed to ensure that equipment and systems are operated safely and responsibly, reducing the risk of accidents and injuries in various settings. A David limit switch is a safety device commonly used in David system, particularly in context of lifeboat and rescue boat launching system aboard ships. Its primary purpose is to prevent over travel or excessive movement of the David arms during the launching or recovery of lifeboats or other marine equipment. The limit switch helps ensure the safe and controlled operation of David system, protecting both personnel and equipment from damage or injury. Here is how David limit switch works and its key features. Limit switch is typically installed on the David structure in a position where it can detect the movement of David arms or other relevant components. It is strategically placed to monitor the travel distance of David arms during launching and recovery operations. Mechanism. The limit switch consists of a switch mechanism often equipped with a lever or actuator that is triggered by physical contact or proximity to specific parts of David system. When the David arm reaches a predetermined position, the switch is activated, signaling the control system to stop the movement of the David or engage safety measures. When the lifeboat is recovered back, that limit switch will activate and stop once the lifeboat has reached its positions. So it will not over travel. That is the main function of that. Functionality already explained why it is used. This much answer will be enough to explain. During normal operation, David limit switch remains inactive as David arms moves with their integrated range of motion. Safety measures. When the limit switch is activated, it sends a signals to the control system of the David, prompting it to halt the movement of the David arms. Same already explained. Protection. David limit switch serves as a crucial safety features to protect the David system, lifeboats, personnel on board ships. Compliance. David limit switches are often required to meet international maritime regulations and standards such as those set by the International Maritime Organization (IMO) and classification societies. Compliance with these regulations ensures that David system adhere to strict safety guidelines for marine operations. In summary, a David limit switch is an essential safety component of David system, providing reliable protection against over travel and ensuring the safe and controlled deployment and retrieval of lifeboats and other marine equipment. Let's move on to next question, question number 8. In engine rooms that are operated under UMS conditions, describe with the aid of sketches how the following are monitored: the perforation of high pressure fuel pipes, periodical maintenance checks and tests required to be done to verify the effectiveness of the system. This question actually I searched a lot of places but I did not get the answer. I searched in the chat GPT answer this. I got some answers but that all are generic. In engine rooms operating under unmanned machinery space conditions, where there may not always be personnel present to visually monitor equipment, including high pressure fuel pipes, perforation detection is crucial for ensuring the safety and reliability of the machinery. Here is how perforation of a high pressure fuel pipe may be monitored in such conditions. Pressure sensors. High pressure fuel pipes are often equipped with pressure sensor at various critical points along their length. These sensors continuously monitor the pressure within the fuel system. A sudden drop in pressure can indicate a perforation or leak in the pipe. Flow sensor. Flow sensors may also be installed to monitor the flow rate of fuel through the pipe. A significant decrease in flow rate or oil irregularities can signal a potential perforation or obstructions in the pipe. Leak detection system. Advanced leak detection system may be employed to detect even minor leaks or seepage from a high pressure fuel pipes. These systems use various technologies such as ultrasonic sensors, laser based detectors, or thermal imaging cameras to identify any leaks based on changes in temperature, sound, or optical sense. Vibration monitoring. An increase in vibration level along the fuel pipe's route could indicate a perforation or structural damage. Vibration sensors installed at a strategic locations can detect abnormal vibration and trigger alarms or shutdown procedures. Temperature monitoring. An increase in temperature along a section of the fuel pipe may indicate friction or heat generation due to perforation or partial blockage. Temperature sensors can be used to monitor temperature variations and identify potential issues. Automated alarm system. When abnormal conditions are detected by any of the monitoring systems, automated alarm systems are activated. These alarms can be audible, visual, or transmitted electronically to alert designated personnel or central monitoring stations. Remote monitoring and control system. In UMS environments, all monitoring data and alarms are often integrated into a centralized control system that can be accessed remotely. This allows operators to monitor the status of high pressure fuel pipes and respond to any issues promptly, even if they are not physically present in the engine room. By employing a combination of these monitoring techniques and system, perforation of leaks in high pressure fuel pipes can be quickly detected and addressed, minimizing the risk of accidents, equipment damage, and environmental pollution in unmanned engine rooms operating under UMS conditions. And to ensure the effectiveness of the monitoring system, certain periodical maintenance checks and tests are essentials. These are calibration checks. Regular calibration checks for pressure sensors, flow sensors, vibration sensors, temperature sensors, and their monitoring equipment should be conducted to ensure accurate reading. Calibration ensures that sensors are correctly detecting changes in conditions and providing reliable data. Functional test. Periodically, entire monitoring system should undergo functional tests to verify its proper operation. This may include simulating various fault conditions or abnormal scenarios to assess the system's response and alarm functionalities. Visual inspection. Although the entire Although the engine room may be unmanned, visual inspection of the monitoring equipment, including sensors, wiring, and control panels, should be conducted regularly. Any signs of physical damage, corrosion, or degradation should be addressed promptly. Data analysis. Continuous monitoring of data should be analyzed regularly to identify trends or patterns that may indicate potential issues with high pressure fuel pipes. Periodic maintenance. Scheduled maintenance of the monitoring system components, including sensors, cables, connectors, and control units, should be performed according to the manufacturer's recommendations. This may involve cleaning, lubricating, replacement of worn parts, other preventive measures to ensure optimal performance. Drift checks involve comparing sensors readings against reference standards or baseline measurement to detect any gradual change or drift in sensor accuracy over time. Adjustment or recalibration may be necessary if significant drift is observed. Alarm testing. Alarm systems should be tested periodically to ensure that they are functioning correctly and are capable of alerting personnel or triggering automated response in event of abnormal conditions. Audible alarms, visual indicators, and remote notifications should be tested. Emergency response drill. Regular emergency response drills should be conducted to evaluate the effectiveness of the monitoring system in detecting and responding to simulated fuel pipe perforation or leaks. This helps ensure that personnel are familiar with emergency procedures and can act swiftly in case of a real incident. I also got one answer explanation in Google when I searched, and the same question you can type in Google and you will get the answer. This is the website from where you can find the answer. There some more explanation is given along with the diagram. You can refer to that. This is the I got from Google. You read and you can make notes from both this answer from the website and also from the chat gpt. You make a combined answer, better answer what you can make. And then now we will moving to the last question with reference to marple annex 4. Draw a biological sewage treatment plan and explain the principle of operation and periodical maintenance checks and tests required to be done to verify the effectiveness of the above system. This answer you can find in my notes, Rahul, page number 40. Let's go to page number 40 of my answer. It's a slight different question. Describe vacuum system, state advantage of the system, state why holding tank may be required to fit it, but the operation, the explanation is same here. See, this is a diagram, and this tank is divided into three parts. One is this part is aeration tank, this middle one is settling tank, and this is holding tank. Now let's see the operation. You can copy this same diagram, it's a easy diagram only. Now see the operation. Raw sewage passes through a commutator into aeration compartment of the sewage plant, where sewage is broken down by aerobic activation. Fluid in this compartment is continuously agitated by air, which keeps the sludge in suspension and supplies the necessary oxygen for purification. The effluent is then passed on to a settlement compartment where the sludge settles out. The treatment effluent passes over into the final compartment for chlorination before discharge overboard. Air is supplied to the plant by means of an air compressor, which should be operational continuously. Excess sludge collected in the settling compartment should be discharged at regular interval, keeping in mind the sewage regulations. Floating solids from the settling compartment is continuously returned to the aeration chamber for further. Oil or grease entering the system kills useful bacteria. Now, what are the maintenance and checks? Aeration blower filter cleaning, blower fan belt tension, checks and renewal, tank cleaning, screen cleaning, tablets to add, UV lamp renewal, blower and discharge pump overhaul, blower oil level check and renewal, vacuum pump inspection, cleaning of vacuum pipelines, aeration tank cleaning, monitoring and maintenance of air release valve, instrument calibration and monitoring, flow meter, pH sensor, etc. If you may like to refer to answers by ChatGPT, you can see here I have given here, screenshot it, and you can take some points from it and add in your answers. This also, these seven points. Then the maintenance also. Point one: routine maintenance, sampling analysis, calibration, sludge management, aeration, system maintenance, pump maintenance, and then emergency response drills and record keeping. So read this and you can make answers out of my notes also and out of this notes also, and make a final answer for yourself. Here we come to the end of the discussion of this question paper. I wish you all the very best for your ETO COC 10 examination.